So the technique for classification that we'll be looking at first is the technique called classification trees. So first of all, let's understand how we can use rules for classification. Okay, so for example, as we've already said, patterns can be of many types. When we say models, models are looking for patterns, and the patterns can be of many types. So for example, I'm giving a very trivial example here, which we've seen before. You've got a data set which has only two columns. The first column is income. The second column is the status of a person, whether the person is a buyer or non-buyer. If you examine this closely, you can easily see that all people with income greater than 65,000 are buyers, others are non-buyers. Okay, so this is one way by which we can predict whether a person is going to be a buyer or non-buyer, or determine whether a person is going to be a buyer or non-buyer, right? It's a model. This is a simple model for determining, given the income, whether the person will buy our product or not. Of course, this is a very trivial sort of example. Real life is not going to be like this. In the real world, we'll have many columns and lots of more rows. So it's not going to be possible for us to just come out with something simple like this. But this contains the germ of the idea of classification trees. Okay, so something a little more complex here. Data set with 3 attributes and the type of car that they own, right? So again, one could look at this and figure out if the income is greater than 200,000, then the person owns a luxury car. If the income is less than 30,000, then the person owns a compact car. You could look at this. And then you could say if the income is between 100,000 and 200,000 and the family size is less than 3, then the person owns a luxury car, etc., etc. We can come out with many such rules just by observing the data. But of course, as you can already see, even in such a small data set, this is starting to get extremely complex. Okay, but if you can do this, if you can identify the patterns, then this is a good way of trying to classify a particular person as to the type of car that they are likely to be owning in this particular case. Okay, so it's possible, and this is the idea of classification trees, right? So essentially, given a large data set which will have many thousands of rows and dozens of columns maybe, we want to have the computer go in, look at the data, and figure out rules like these that work well. Okay, of course we have things to do here. We want to define by what do you mean by a rule working well. Again, as I've said many times, we cannot expect the rules to be perfect, right? There will be mistakes. The point is it still useful or not? That's the point. Okay, of course, as I've said, the rules can involve many attributes. Okay, again, as I've said, do not expect the rules to be perfect. Okay, so here I've got a slightly modified version of the same data that we looked at earlier. We're saying if income is greater than 65,000, then the person is a buyer, otherwise a non-buyer. But it turns out that that's not exactly correct. Here you have, in the first case, you have a person whose income is pretty high, but the person didn't buy. And in the last case, you have a person whose income is less than 65,000, but the person bought. So by and large, the rule works, but it's not exact. Okay, and this is all we can do in the real world. Let's take this very simple example and look at it as if it were a classification tree, right? So what we're saying here is, well, we're looking at income as the criterion to determine whether a person is going to be a buyer or non-buyer. And of course, the level at which we are dividing the income is 65,000. That we've just done that based on observation. And we said if the income is less than 65,000, then what you're seeing is that there are 2 buyers and 1 non-buyer, right? That is, we said earlier, we had said if the income is greater than 65,000, then buyer, that's what you're seeing here, greater than 65,000. But it turns out that if the income is greater than 65,000, then the person is not necessary, that it's not guaranteed that the person will be a buyer. But it turns out that 2 of the people of the 3 who have that characteristic of income being greater than 65,000, 2 of them were buyers, 1 is a non-buyer. And in the case of the income being less than or equal to 65,000, there are 10 such cases that satisfy this condition. And out of those, it turns out that 9 of them are non-buyers, only 1 is a buyer. Okay, so we've got a rule which is this that you're seeing on the slide. And the rule works well, pretty much. Okay, it's not exact, but in each case, if the rule is great, if the income is greater than 65,000, we see that the majority are indeed buyers. And in this case, the majority are indeed non-buyers. Okay, so we can say with a certain degree of confidence that our rule is good, but we cannot say that the rule is exact. Okay, so what we will do later on as we go forward is to say, well, if the income is greater than 65,000, instead of saying the person is going to be a buyer, what we'll say is the probability that the person is a buyer is 2/3. Okay, that's because there are 3 cases that satisfy this condition, and 2 of them are buyers, 1 is a non-buyer. So we are going to say the probability of a person being a buyer is 2/3, and of course, the probability of a person being a non-buyer is 1/3. And in the second case, we are going to say the probability of a person being a buyer is 1/10, because there's only 1 buyer out of the 10 cases. And of course, the probability of non-buyer is 9/10 or 0.9. Okay, so this is what we meant earlier when we said that classification models first identify a probability, right? And then it's up to us to convert the probability into an actual classification through the use of a cutoff probability. Now let's consider that this is a tree, and we'll talk about why we call it a tree. Okay, so there are 2 nodes. That is, you can either land up here, that is, you're given a person and you're given their income. Now you can use this model to figure out whether the person is going to be a buyer or not by running them through this decision tree. Okay, so if the income is greater than 65,000, they end up here, and we say, well, the probability of them being a buyer is 2/3. And if they end up here, then we can say the probability of them being a buyer is 1/10 or 0.1. Okay, now I just want you to think about how confident would you be in the decision if you reach here or if you reach here, right? You're saying the probability is 2/3, right? How confident would you be that this probability is quite accurate? And how confident would you be that this probability is accurate? Which of them do you think is something in which you will have greater confidence? Okay, that's worth thinking about for a little bit. I would say pause the video, think about it, make up your mind as to what you think it is, and then continue the video. Okay, so what you should note here is that in this particular case, the decision, the probability is being determined based on only 3 cases, right? That because only 3 cases satisfied this condition, and the probability is being determined only based on 3 cases. That's a very small number, right? For example, if our data set were slightly larger, then the thing could completely turn out the other way, right? It could turn out that there are more non-buyers here. Who knows? Okay, so this is something that is very fragile because it's based on a very small number of data points, whereas this one is based on quite a relatively larger number of data points, because there are 10 cases that satisfy this particular condition. And therefore, we would feel a little more comfortable saying that a person whose income is less than 65,000 will not buy the product than we will be in saying a person whose income is greater than 65,000 will buy the product. Okay, so that's what we are saying. So ideally, what we want is we want these probabilities to be calculated based on relatively large numbers of cases. Okay, I'm just highlighting this at this point. We will return to this later when we learn exactly how such trees are constructed. You know, how does the machine learning process go about constructing such a tree? At that point, this concept will come back and be useful for us. Okay, so here's an example of another tree, classification tree. This time the tree is only showing you the actual decisions, right? It's not showing you the number of cases which meet each of the classes. The 3 classes are low, medium, and high. And this is an example I created for determining whether a prospective student will be a low performer, medium performer, or a high performer in college, for example. Okay, and I built a classification tree to determine that based on some historical data. This was, of course, data that I just made up, not any real data. Okay, And in this case, I'm not showing you, for example, the first criterion we're looking at is the SAT score less than whatever, 1220? And if it is yes, if a person has an SAT score less than equal to 1220, we are looking at and saying, is the SAT score even further less, 750? In that case, we are saying 950. In that case, we are saying the person's performance is low. But we are not showing here how many cases who satisfy this condition have a low performance, medium performance, high performance. Okay, as opposed to the previous case where I showed you the probability, or I showed you the mix in each of the cases. In this example, I'm not showing that. Okay, just to point out. So this example is simply telling us that for each of the endpoints, it is simply telling us which class happens to be the majority, right? So for example, let's say that you've got a person whose SAT score is less than 1220 or greater than 1220, right? Because we say no. Okay, they have a high SAT score, and then we're looking at their SAT score is of course between 1400 and this, and is greater than 1400 as well. Okay, this again, because when you go to the right it is no, when you go to the left it is yes. That is a general tradition. So here are people whose SAT scores are greater than 1400, and we are classifying them as potentially high performers. Okay, so let's assume, for example, from our data set that there were 300 people who satisfied this condition of SAT score being greater than 1400. Okay, so there were, let's say, 300 people who satisfied the condition. Not all of them actually ended up being high performers in the college. Again, all of this is based on historical data, right? So we know what their SAT score was, and we know many of the other attributes, and we also know how they actually performed in college. Okay, so it's not as if all the people with this particular characteristic were high performers, but the majority of them were high performers. Okay, so there might have been some people who performed at a medium level and some people who also performed at a low level, but this tree is classifying them as high because the majority of them were high. Okay, so I'm just showing you that sometimes you will have trees in which the actual proportions are not shown, just the classification is shown. Okay, that's just another example. So in this lesson, you've looked at the notion of what is a classification tree, and we have looked at how in a classification tree you can run a particular case through the tree and then assign it a probability of belonging to one class or the other class, or one of several classes if the example has several classes, right? So we can either do a classification based on majority class, or we can be more sophisticated, calculate a probability, and then using other techniques convert that probability into an actual classification.